So I promised earlier in the course that we were going to talk more about drag, and so that's exactly what we're going to do today. So if you recall, we've talked a lot about kinetic friction and static friction, and very briefly I mentioned drag. I think I mentioned air drag, but there's actually drag whether you're in air or other types of fluids as well, like water, for example. And basically, there's two types of drag that are relevant in two different situations, as I'll describe. There's viscous drag, which is relevant kind of at low speeds, and then there's non-viscous drag, which is relevant at high speeds. So one year when I was teaching this course, we used this free OpenStax textbook, which is very good, and you know their summary of these two things is that suffice it to say that the drag is relative to some kind of velocity of an object in a fluid, and because both of these types of drag depend on what the velocity is. I think I mentioned earlier that the kinetic and static friction don't care what the velocity is, but these types of drag do, as I'll explain in just a moment. So this is non-viscous drag, which again is relevant at high speeds. And by high speeds, I mean, for example, this drag dominates the friction when your car is driving down the highway. You'd think that for example, like, the friction on the axles spinning around, the ball bearings, you might imagine that would be where a lot of the friction goes. But no, that's not true. It's actually most of the energy that you use up with your car is to push against this force, which comes from the fact that the air, the faster and faster that you go, the more air slams into the front of your car, and the faster that the air is going, that slams in your front of your car. And so the force that your engine has to overcome in order to travel at 60, 70, 80 miles an hour, whatever, is this. And so it depends on the area of your car, the cross-sectional area. So, for example, a lot of race cars are sort of lower to the ground. Like the extreme example is Formula One, is all the way down almost to the floor. So the less area, the less cross-sectional area, the better. A lot of the experimental, like maximum speed, 500 mile an hour type demonstration things, they are not only are they low to the ground, they're also very skinny. So Ohio State has what's called the Buckeye Bullet, which is a world record holding electric car that has a maximum speed of over 200 miles an hour, 300 miles an hour. I forget exactly how fast they managed to get the thing. But the thing is like this, it's almost this cylinder on wheels. And what they're trying to do is decrease the area as much as they can. Which is important because the area is one of the few things that you have the ability to change, because there's the speed here. The speed is whatever the speed is going to be. So if you're traveling at 60 miles an hour, 60 miles an hour squared, 70, 80, whatever it is, this thing squared, it gets bigger and bigger. So there's, as we'll talk later on, if you want to go twice as fast, it's going to be 4 times as much force. So it's really hard to go really, really fast. Now, there's also the drag coefficient. This has to do with the shape of your vehicle, the shape of whatever object is moving through this fluid. And if it's a very smooth and pointy shape, think like, I hate to say like a missile. If it's smooth and pointy, a missile, a rocket going up into space, then the drag coefficient will be nice and low. And the next slide, I think I'm going to give you a table of the drag coefficients. The last thing is the fluid density. And so if you're going through high density, then that's going to be even more of a drag force. So for example, submarines traveling underneath the water, they move much more slowly than boats do on the top of the water, for example. And it's because the boats don't really have to push against the water so much, they just have to push against the air, and the water is just there to help them float. Whereas the submarines, they have to shove the water out of the way in order to move that fast. So that's one thing that comes into play there. I think this next slide has drag forces. The hilarious thing to me about this table, which again I got from the OpenStax book, which is another good book. You should check it out for more example problems and things. The thing I love about this table is that in terms of the drag coefficient, right, which is this thing here, this big C, the drag coefficient, Ferrari Testarossa has a drag coefficient of 0.37, and you can see how like pickup trucks have higher drag coefficients because they're just so boxy and flat, I guess, and instead of smooth like a Ferrari. But the hilarious thing is like the Honda Civic and the Toyota Camry have a lower drag coefficient than a Ferrari Testarossa. And my car in particular, Priuses, I don't have a Prius, but I have a Nissan Leaf, which is similar. If you look closely at that car, it's like the whole, from the windshield down to the nose of the car, it's all flat, and that is designed to try to make things as smooth as they can in order to decrease this drag coefficient, which ultimately decreases the force, which decreases the amount of energy that the engine has to put out, which can increase your gas mileage or increase the range of your electric car, if that's what you have. But if something is mostly flat, if something is mostly flat, like a circular flat plate, this drag coefficient is pretty close to 1. Basically means that like all the air is hitting this thing as a flat thing, and if it was much more pointy, this would be much lower, but the air is just slamming into that thing, and having something much smoother would be better. So sometimes when we do example problems, I might tell you just to assume a drag coefficient of 1 for anything that's very, very flat, Okay. Now for low speed, instead of having this thing with all these different terms, we often have something like this that, unlike the non-viscous drag, it's proportional to the velocity to the first power, not the second power. Some people would call this turbulent drag. So if you're an aerospace engineering major, you may see this described as turbulent drag in the future. Different names for the same thing, in my opinion. This is viscous drag, so this is at very low speeds, is what you get. And this is actually going to come up later, because eventually we're going to talk about springs that are oscillating, and maybe those oscillations are on water. And this gives you a drag term that is easier to deal with mathematically than this. Just, it so happens. So how does this all work together? Well, for some object, let's say, below some speed, the drag force is going to be linear. And so it's going to be what I call viscous drag. It's not that the normal drag doesn't exist below this point. It's probably hard for you to see, but there's these little dots here. The normal drag, the non-viscous drag, is still there. It's just that it's not as big as the viscous drag. And so you add the two together to get the total drag force. But above some velocity, and don't quote me on, this velocity at which it changes depends on the shape of the object, how big it is, how the area, how pointy it is. So this is not a general rule, but at some point, above a certain velocity, the normal drag, the non-viscous drag, takes over, and the sum of these two velocities lines up very closely to the normal drag. Again, both drag terms are always important, but there's regimes in which one is much more important than the other one. So for engineering applications, so earlier I was saying high speed, right? So high speed, low speed. It's a little bit more complicated than that, but for large objects moving in air at high speed, you want to use the non-viscous drag, aka turbulent drag. So in other words, large objects moving in low density media. If you're landing on Mars, it's not going to be air, it's going to be a bunch of carbon dioxide, but it's still low density media, and so the non-viscous drag is what matters. So again, large objects moving in low density media at high speeds is non-viscous drag. Small objects moving at low speeds use the viscous drag. So for example, there's people that do research on how it is that honeybees can fly, because they are a small object and the speeds are slow, that it's viscous drag that matters instead of the non-viscous drag. And so honeybees fly very, very differently than, say, birds do, which are larger objects moving at higher speeds. So for bugs moving in air, you want to use the viscous drag. But also the viscous drag is relevant to denser liquids like water or oil, those kinds of things. And I'm going to give you another example of viscous drag in just a second. I think it's on the next slide. So in today's worksheet, so non-viscous drag, right, the high-speed drag, this drag is what determines like the top speed of whatever vehicle you're thinking about. So we have a worksheet today talking about how you're trying to take this vehicle and get it to increase the maximum speed. And you're asking how much more horsepower of an engine do we need to get up to a maximum speed, assuming that this non-viscous drag is the main thing that's preventing us from getting up to higher speed, which is actually very good, very close to true. You can also use a non-viscous drag to figure out the range of electric cars. Like I said, most of the energy in your car, whether it's in the form of gasoline or in terms of electricity, chemical energy that's converted to electric, the range of cars, most of the energy in your car is not actually used to accelerate your car up to a speed. Most of that energy is to keep your car going at that speed. Because to keep your car going at that speed, it has to shove all this air out of the way, and that takes a lot of energy. So there's another worksheet. I don't know if we'll cover it today or if it'll just be extra, but you can also think about fuel efficiency and how that depends on velocity. That worksheet talks about how if we were to increase the speed limit in Ohio from 70 to 75 or something like that, I forget if it's 70 to 75 or 65 to 70, but if we were to increase the speed limit, what would that do to fuel efficiency statewide, and so potentially how much more oil will we need as a state to be able to sustain that. Another aspect of application of non-viscous drag is that as you're getting off on an exit on the highway, as soon as you put your foot off of the gas pedal, you'll notice the car starts to slow down at least a little bit. And that's actually because the air drag is slowing your car down. And so that is a perfectly good example of non-viscous drag. So you have your car, right? You have the drag force on it, and so the car is going to, that's an unbalanced force, which is going to produce an acceleration opposite to the direction that you're going. So non-viscous drag is a pretty good application of that. Okay. The next slide starts to talk about terminal velocity. And so terminal velocity is relevant both to non-viscous drag as well as to viscous drag. And actually the next example is actually viscous drag. Terminal velocity is a very fancy word for the maximum velocity. And so this is a little video of these little single-celled organisms, and what's hard to see is that they have a little tail that they push on the water so they can go in the opposite direction. And so you can see them kind of moving around. The flagella is the fancy name for the tail. And the harder that flagella swims, you can think of the flagella as sort of just exerting a force on the water, right? Because it's pushing the water that goes by as quickly as it can. But the thing is that because it is so small and because the fluid is so dense, that means it's the viscous drag that matters instead of the non-viscous drag. So this is a little code that I made, which is not really for anything. It's just I think you'll find it interesting, which is that this little circle, let's see if I can, so there's a little code here. I can show you what the code looks like if you want. So there's a force here. There's a force here that can produce an acceleration, but there's also a drag term, and the drag term is B times the velocity in x direction. So this is classic viscous drag. There's also the same thing on y. I have exactly the same thing on y just for fun. But here is the little circle. This is our little flagellum, or whatever you want to call it. And so if I press right arrow, if I can click this thing and then press right arrow, there we go. So the red thing is the velocity here. So you can see the force that the forward-going force from the flagellum, from the swimming action, is a little blue arrow that's a little hard to see. That's right there. Do you guys see that? It also shows a yeah. And if I let go, it'll come to a stop, right? Because there's a drag force. It's unbalanced. There's no force pushing in the opposite direction. It's just eventually it's going to come to a stop, right? But the terminal velocity is the maximum velocity this thing can do. Do you see how this red velocity here, this line sort of comes up to sort of a maximum there? It says velocity right below the screen. I'm sorry you can't see it, but so this is sort of a max velocity. It does not continue to go faster and faster and faster is the point. So it reaches some maximum velocity, which we call the terminal velocity. The special thing about the terminal velocity is that because the velocity is constant, that means the acceleration is zero. The acceleration being zero implies that either there are no forces, which in this case is ridiculous, or there is more than one force that are in balance. And in this case, the forward-going swimming force from the little wiggly thing called the flagella is balanced by the drag provided by this fluid, which is water. And so those two things are in balance, and so we end up with getting zero acceleration, constant velocity. That is just for, yeah, you can see how it slows down. If I let go, eventually it comes to a stop. So again, that is for the viscous drag. It's not too hard to modify this program to get it to do the non-viscous drag, the drag that goes v squared. You're welcome to do that just for fun, not for any credit. But that's the basic idea of terminal velocity. Okay, so if we are traveling at the maximum velocity, aka the terminal velocity, then the force that's exerted to swim is going to be the same as the drag force that's pushing back at us, right? Because as we're going initially, this force is more than that force, and we're accelerating, right? So you can see this pink-purple acceleration thing here. But as we start to go faster, remember the drag term depends on the velocity. The drag term gets larger and larger, and eventually these two things equal each other, in which case the acceleration is equal to zero. What's interesting is that we can actually calculate what velocity this happens at, because if this is zero, that means these two things are equal to each other, and the maximum drag force in this case is just the drag coefficient times the maximum speed. And so to solve for the maximum speed, it's pretty easy. You just the maximum force that our little flagella can do, divide by this drag coefficient, whatever it is. If you want to know what this drag coefficient is, you know, that's for more advanced classes in aerospace engineering and stuff like that. Same thing with the drag coefficient C as well. So it's pretty easy, pretty interesting relation. And if you wanted to, you could actually take this, compare it to the result of the code, and just make sure that that works. And that would be an interesting thing to do. It won't make you do that, but it's not too hard. Okay, so we can also do a terminal velocity calculation with a situation. You can think of it as skydiving, jumping out of an airplane, jumping off buildings, which was called base jumping. Either way, you have a situation in which there is a force. In this case, it's the weight pulling you down. It's a constant force. Remember, the flagella was a constant force in the water. Well, the weight now is a constant force downwards here. And then there's also the drag pushing upwards, right? Because you're going faster and faster, the drag is going to be in the opposite direction. So this is a code. This code is actually, it's not based on skydiving. It's based on the idea that if you drop a bowling ball off a building, which I do not recommend, as long as the camera's recording, I'm going to make sure to go on the record that that's my recommendation. And so there's a bunch of variables up here. There's a bowling ball mass is about 7 kilograms or so. The area of a bowling ball is not huge. You can see the density of air is about 1 gram per meter cubed. And then for the coefficient, I just assume 0.5. 0.5 is usually a good guess. I think on the earlier table that I showed, it said that spherical shaped things has a drag coefficient of 0.4. So this is sort of in the neighborhood of that. For my purposes, it doesn't matter, but if I was an aerospace engineer, I would never say that. But so you can see that we're advancing the y position here, and there's forces involved, and importantly, there's the weight mass times gravity, where g is positive. There's a minus sign out front to make sure that that force is downwards. And then there's this drag term going in the positive y direction, and you can see the coefficient, the factor of 1/2, the density, the area, and also the velocity. Importantly, the velocity is squared. That's why there's the vy times the vy. So I can press play on that, and if you click the screen, then that allows the ball to drop, like so. And it's the same ball, I just have this one stationary just so that it's easier to see what's going on. So let me try to do that. There we go. So I'm not actually visualizing the drag forces just because that would make it look a little bit on the complicated side. But you see the thing fall, you see the red velocity arrow get larger and larger. But it's not a constant acceleration like it would be for projectile motion. That would, in that case, the acceleration would be flat like this. Instead, the acceleration gets less and less as we kind of approach this terminal velocity. Now, we never quite get to terminal velocity here in this code because just not enough time passes before we get to the bottom of the building. But a fun thing to do is to press space bar, which if you look in the code, opens up a parachute. So the cross-sectional area of the bowling ball is pretty small, but if you click spacebar after you drop it, spacebar, now the area is much larger, and we reach this terminal velocity. You notice that this velocity is nice and constant, and we can actually go and we can try to calculate what that velocity should be, and we can double check the result of this program with that calculation. Okay, so let's try to do that. So it's similar to what we did a moment ago, right? So the parachute comes out there. Then we eventually reach terminal velocity. So it's similar to what we did earlier. I think this is Tom Cruise from Mission Impossible Fallout. So there's the weight pulling Tom down, but then there's the drag force pushing the opposite direction. And at the terminal velocity, those two things balance each other out. And so the acceleration is actually 0. So even though you're falling at a constant speed, right? So AY is not equal to 9.8. AY is equal to 0 here. And so this drag force is equal to the weight. And because of that, we can calculate what this velocity, this maximum velocity would be. And so because we know what the drag force is. And so we can sort of rearrange this, multiply both sides by 2, divided by C rho A. Take the square root, we get this, which is very similar to what we found before, except that on the top, instead of having F exert of what this flagella was doing, now we have just the weight of the person. Another difference is that here we have the density of the air, whereas the flagella was dealing with the density of water. So that's a big difference. The density of air is about 1 kilogram per meter cubed, whereas the density of water is 1,000 kilograms per meter cubed. And so because rho is much smaller, Vmax can be way bigger in air than it is in water, for example. Also make sure to, so you don't want to hit the ground at this speed, right? You don't want to hit the ground at this terminal velocity. I forget exactly what terminal velocity is for a skydiver, but you can calculate it here. But you definitely want to increase the parachute. to slow your terminal velocity down, so you can land on the ground at hopefully a few miles an hour instead of 200 or something, or whatever it is. At this point, I should probably tell you that there is a skydiving class at Ohio State. Um, I would not recommend it, but it's there so that you know. All right, so there we go. Now, what's interesting is that the terminal velocity is a function of mass. So if you notice that for everything else the same, heavier things fall more quickly because the terminal velocity is larger. And so a fun demonstration of that is to take coffee filters, those little pieces of paper that people use to filter coffee, and you put one paper clip, two paper clips, how many paper clips you want to put. You will find that the coffee filters that have more paper clips on them, the area of that coffee filter is the same, right? But the mass attached to it is more and more and more. The fluid is the same, right, because it's always air. The shape of the coffee filter is the same, so the drag coefficient is the same. So you should find that the more paper clips you have, the faster that the thing is going to fall to the ground, and that's what this experiment shows. And so you see there's, I guess this is not so much a coffee filter as it is like a muffin tin type deal. So you put how many paper clips on, so this experiment, so this one has 7 paper clips attached to it, whereas this one is only like 1 paper clip. And you can just see that the 7 paper clip thing falls much faster than the 1 paper clip thing. So there you go. It's a fun experiment that people like to do. I won't make you guys do it, but what I will make you do is one of the experiments we're going to try to do is to drop a ping pong ball, this is the reason why you have ping pong balls, by the way, because it is something that has a known coefficient, right? It's a sphere, but it's very lightweight, and so the drag force, which is ordinarily small on falling objects, the drag force is larger relative to its mass, and so it has a nice small area. Well, it has an area to it, but the mass is small, which means that the terminal velocity is more close to the velocity it might get as it's falling. So one of the things that I hope that we can do this semester in lab is to have you drop that ping pong ball, hopefully in front of like a meter stick, and to be able to show that it's accelerating at, maybe initially it's accelerating at 9.8 meters per second, but by the time it's getting closer to the ground, it might be accelerating less than that because of the drag, which is very much like the situation with the base jumping, right? So it's falling, but by the time it hits the ground, the acceleration is not 9.8, it's something less than that. It might be -5 meters per second or something like that. But that's the basic idea that I'd like us to be able to do. Now it's going to be tricky because it's quasi straightforward to get velocities from this. It's medium difficulty to get accelerations from things that are moving. It's even harder to figure out an acceleration that changes with time. So you're going to have to use all of your chops from analyzing videos like these to be able to detect that the acceleration is changing, which is pretty cool. I think this is going to be fun to do. So that's the end of the lecture. There's some worksheets for you guys to work on, but that's all I had for today.